section 5.2. And it is the addition rule. And the rule of complements. Can y'all see? Okay. Okay. And let's see what we're going to do in here. We're going to compute probabilities by using the general addition rule. We're going to compute probabilities by using the addition rule for mutually exclusive events. We're going to compute probabilities by using the rule of complements. I'm not going to make you write all that out. Let's do it. Let's start with a definition. A compound event is an event that is formed by combining two or more events. Guys, like a compound sentence. Compound sentence has and, or, but. Okay. This one will look like the probability of A or B equals the probability that A occurs or B occurs or both occur. Okay. And honestly, we start off with this, it's friendly. It's like what I like to call friendly. We have a chart. You just got to be able to read a chart. And actually, I was really happy. I was pleased with y'all's ability to read charts on Unit 1. Lots of times, we'll have students that it is very difficult for them to read a chart, to read a graph. But y'all didn't have really any trouble with that. The only one that gave you trouble and that I had to clarify some was the one about the movies. And which one was the movie, which one was the frequency. And so like 0 movies was on the x-axis on the bottom, and the frequency is the number of people that watched 0 movies. The number of people that watched 1 movie, 2 movies. That was the only graph that gave y'all trouble on the Unit 1 exam, which I was very pleased with that. Of course, also asking you questions about, there are a lot of you that spend the majority of your day reading charts and graphs in your jobs. That helps explain to me where that came from. You make money and keep a job because you read somebody's chart correctly. You kept somebody alive. Thank you. That's nice that you do that. It also makes your statistics grade better because you can read a chart. And so these will be fairly easy for you because you can read a chart well, okay? That was my whole long stint of that. Example 1, use the following table. I was really just happy with y'all. Y'all made me like, teaching stats is never one of my favoriteest things to do because people just don't like it. People don't want to be here. And then so things don't always turn out on a test like they're supposed to. But y'all made me happy. The following question. I seriously had put off grading your test because I was like, this is going to make me sad. And I didn't want to grade it and put the grades in there, and then it would make you sad. But then you didn't make any of us sad. Good job. Use the following table to answer the following questions. Oh, that's nice of them. Okay, so we have likely, I need to move that down a row because I've got a header over here. Likely to vote. Okay? And then we have not likely to vote. But then we split that up a little bit here. And so we have people that are likely to vote that are in favor of whatever's happening. Okay? There's 372 of those people. And there are 151 people that are not likely to vote who would be in favor of it. Whatever we're voting on here. Okay? Then we have those that oppose it. And there are 262 people that are likely to vote that oppose what's going to happen. And there are 103 people who oppose, but they're not likely to vote. Okay? Then I have the undecided people. Okay? And of the undecided people, there are 87 people that are undecided that are likely to vote. And there are 25 undecided people that are, what in the world? Look at it. Oh my gosh. Okay. Okay, it has been going a little, okay. Okay. That means it's tired. It wants us to go home, doesn't it? I'm going to fix it. 262. What you had there was right. I was just trying to make my chart look a little better. And then now it's doing very strange things. Okay, 87, 25, 262, 103, 372, 151, 103. Okay. Oh, and now it's double written over it. I'm sorry. Okay, we're just going to go. Y'all know what it says, right? Okay, I'm sorry. We're going to get through that problem because it's going to make me go blind staring up there at it. Okay, so that's awful. A says, what is the probability that a randomly selected adult is likely to vote and favors the law. Okay. Well, the first thing we need before we find that probability is we need how many people there are, right? How are we going to find out how many people there are? Add them all up. Yeah, y'all add up the 372, the 151, the 262, the 103, the 87, and 25. Y'all tell me the total number of people. Thousand total people. Good. Now, we want how many are likely to vote and favors the law. Which number is that? Can you read that chart and tell me? Yeah, 372, right? This 372 right here, they favor the law and they're likely to vote. So it's like you're going down and across. You go to the favor people. There's a 372 under favor and there's a 151 under favor. The way I know is I'm looking who intersects with favor. And it's the likely to vote. Likely to vote and intersects with favor, right? Okay, and that's what we needed, so it's the 372. Okay, so I've got, that means the probability of likely to vote and favor is going to equal 372 out of 1,000 people, which should give me 0.372. You agree? Because you're just moving that decimal 3 places to the left. All right? And I kind of fixed the chart. Let's look at B. B says, what is the probability that a randomly selected adult is likely to vote? That's all. There's no and there. It's just likely to vote. So I'm looking for a probability of likely to vote. Okay. Total still the same. I still got those 1,000 people, right? Okay. Now I need to know likely to vote. Well, how many things do I need to add up some stuff? Is it just that 372 I have highlighted? What do I got to do? Good. That's going to be my 372 plus the 262 plus 87. Okay? All those people are likely to vote. Some are likely to vote and are in favor. Some are likely to vote and oppose. And some are undecided. I got to fix that. Okay? But they are all likely to vote. Y'all add those up for me. 721? Good. So I have 721 people out of 1,000. That's actually pretty good. Out of 1,000 people, 721 are likely to vote. Of course, that is 0.721, which is about 72% of the population. That's not bad. Okay. Let's look at C. C says, what is the probability that a randomly selected adult favors the law? Okay, so the probability of favors. All right, is it just the 372? No, because favor says there's 372 that favor and there's 151 that favor. It's just those 151 are not likely to vote, but they still favor. Okay? So that's going to be 372 plus the 151 all over 1,000, which is going to give me what, 523? Good, over the 1,000, which is 0.523. Okay. D says, find the probability that a person is likely to vote or favors the law. Okay? So we're likely to vote or we favor the law. My question is, can we just add likely to vote and favors together? Let's think about it. Let's try that. Because it says you're likely to vote or you favor the law. Okay, so that means both. That means you, or kind of means add here, okay? So let's see if that works for us. If we were to say the probability of favors plus the probability of likely to vote, let's see what happens. That's probability of favors is 0.523 plus the probability of likely to vote is 0.721. What does that give me? $1.244. There should be a big alarm going off in your head right now. Can we have a probability over 1? Nope. This is bad. Bad news. Bad news. Can't happen. Why? What happened there that we got a probability over? Why did we get a probability over 1? We did what they said. We took the probability of favors. Which, what did we do with the probability of favors? We said 372 plus 151, right? And then what did we do with likely to vote? We said 372, 262, and 87. So what's the problem there? We use these two for favors. We use these three for likely to vote. What did I do wrong? I counted that 372 2 times because he's actually a favor and a likely to vote. And if we just add the probabilities like that, you've counted those 372 people twice. You counted them in the likely to vote, and then you counted them in the favors because they are likely to vote and favors people. Okay? So, it helps us come up with a rule, but let's look at the table and see what we have. If we want the probability of favors or likely to vote, okay? All right. Well, that means I need to list all the people that are likely to vote, and then any number that I haven't already listed that goes into favors. So what I'm doing is I'm adding 372, 262, and 87. Let me make this smaller so it all fits on there. 372 plus 262 plus 87. Those are all my likely to vote people. Now let's talk about the favors. The favors are 372 and 151, but I've already listed 372. I've already counted him. I went check, check, check. Now I need to list the favors people. Well, I've already got a check on the 372 plus 151. Okay? That's all going to be over the 1,000 people, right? Which, what does that wind up giving me? 0.872? 0.872 when I divide by the 1,000, right? Because you get 872 over 1,000. Okay, that looks better. That's less than 1. We're okay with that. So, here's the deal. What you've proved right here is you've proved the general addition rule, okay? So the general addition rule states that I have the probability, if I have the probability of A or B, it's going to equal the probability of A plus the probability of B minus the probability of A and B. That's subtracting that second 372 off over there. He's the one that caused the problem. He was both. The 372 people that favored and were likely to vote, they were the problem. They got counted twice. We got to subtract them back out one time. Okay? This is a very important rule. Okay? Because if in a minute we find out, well, pretty much what you have here is this information is not what we call mutually exclusive. Okay? Because those 372 people fall into two categories. They're likely to vote and they're voting in favor. Okay, so you can't just add their probabilities together. You've got to look for those things there. Okay? That was D. So let's do, there is a part E. E says, use the general addition rule. To find the probability that a randomly selected person is not likely to vote or is undecided. Okay. So, and it tells me specifically here that I should use the general addition rule. I'm going to lasso this and I'm going to move him to the other page so I have enough room. I'm putting him back, I promise. Okay. Okay. So, general addition rule says that the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Okay? So, let's fill in that A and B, okay? So, a randomly selected person is not likely to vote or is undecided. So, I'm looking for the probability of not likely or undecided. Okay? So, that is the probability of not likely plus the probability of undecided minus the probability of not likely and undecided. Okay. So I go back to my chart that I wrote way up there because we're still on example 1. So, let's think about, we got to do the probability of not likely. Okay, so what all do I add together for not likely? Good, 151, 103 plus 25, right? Those are all my not likely to vote people that are right here. Okay, not likely to vote, 151, 103, and 25. So that's all over 1,000, correct? Okay, that's probability of not likely. Now I need to do the probability of undecided. So I go back over here. Here's my undecided column. Who all's in there? What do I add up there? 87 in the 25 plus 87 plus 25 over 1,000. Okay? Now it says subtract off the probability of not likely and undecided. So that's that one number we had right there of not likely and undecided. Which one of those numbers is that? The 25. Good. And guys, if you're not certain, look back at those other two fractions where you were adding. What number's in there 2 times? 25. In that first set of fractions, I got 151, 103, and 25. In the second fraction, I've got 87 and 25. Who wound up being doubled? The 25. So we got to take out one of the 25s. If you're not sure from that chart of who you doubled, who you're looking at right there, you wrote it down, guys. It's there. You got the double there going on, okay? So, your calculator is fancy enough that you can put in parentheses. You can actually make a fraction bar in there, can't you? Yes, we can. You should be able to in your, you don't know how to do that? Math? No. Let's see if I have the, do y'all remember? Who remembers how to make it like a stackable fraction? Come on, Robert, you're the one that usually knows that. Not this time. Oh, here. I found it. Yeah, okay. If you go to, if you'll press, no, not that. Where did I go? If you'll press math, it's right, see there's the second button, alpha, and then math. There's y equals second button, alpha, and math. Everybody find it? Go.
What?
Math. Go to math. Go over to frac.
Oh, there it is.
And you want number 1, ND, numerator over denominator. Look. Now, it lets you do that. So you can say 151 plus 103 plus 25. And then you can make that little fraction all over 1,000. And then go to the side and say plus. Y'all want me to put that on the... Are y'all with me?
Then I do it again.
Yeah, you got to do it again. Do you want me to put it on the screen or y'all got it? Screen? I heard screen. Okay. You know time I get over there with my slow self. Okay, let me go to, oh no, I moved it over to, no I didn't, there he is, okay. I pop him up. Okay, so I am going to math. See the math button right there? And then I go over to frac and do number 1. And so then I'm putting in 151 plus, is it going? Yeah. 103 plus 25. And then I use the down arrow right there. And then I can put in the 1,000. Okay. Now, to get out of that, arrow to the right. Okay, and see how he's sitting beside? Then you're going to say plus. And then you can do it again. Go to math. Frac 1. And this time I got 87 plus 25 all over 1,000. Okay. Then we go minus math. Go over to frac 1 again. And then I got 25 over 1,000. Okay. Hit enter. Gives me 162 over, that's not right. Oh, that should be, that's not right.
Mine says 183 over 500.
What did I type in wrong somewhere?
You got 1033, so 130.
That's it, thank you. I can hit enter on that and then I can go in there. Well, I say I can, yeah, I can. Okay. That would be why he looks like that. Delete. Oh my gosh. Okay, guys, y'all are just, you knew I wasn't going to be able to run this thing up here. Okay. $183 over 500. Is that what y'all got? Okay. Now, you need to write that as a decimal, right? You can actually retype it, or you can, let's see, if I go back to math and I go to decimal number 2 and I hit enter. So it's taking my answer and it's going to convert it to a decimal. I hit enter again. I get 0.366. Is that what y'all got?
Yep.
Alrighty. Oh. 0.366. Okay. Good job. All right. And we used our general rule of addition there. Let's look at example 2 now. Example 2 says, we got a big chart here. So, first row says managers and professionals. Okay. Second row is service. Third row is going to be sales and office. Fourth row is construction and maintenance. And fifth row is production and transportation. There it goes again. Okay. All right. Then I'm going to have a column titled non-college. And then one titled college, of course. Okay, managers and professionals that are non-college is 17,564. Managers and professionals that are college is 31,103. Service, non-college is 15,967. College is 2,385. Sales and office, 22,300. 7,352 non-college and 7,352 college. Construction and maintenance, 12,511 on non-college, 1,033 on college. And then production and transportation is 14,597 in non-college and 1,308 in college. Okay. A asks me, what is the probability? I'm going to abbreviate it. That a selected worker, we're going to say that a worker is a college graduate. Okay? So we of course need to find the total number of participants here that we're talking about, the total number of people. So in order to do that, what am I going to do? Add them all up. Because seriously guys, they weren't nice. They didn't tell us. I'm not hiding that from you, I promise. What'd y'all get? Good. 126,172. 126,172 is the total number. Now, we want the probability that they are a college graduate. So, probability of college. So, which column am I going to add up? Yep. So, I've got the 31,103 plus the 2385 plus the 7352 plus the 1033 plus the 1308. How many did y'all get? $43,181. So I've got 43,181 over the 126,172. Okay, so divided by 126,172. 126, not 123. And are we getting 0.3422? Or 0.342? So about 34% of the people that they surveyed, polled, had college degrees. They were college graduates. Okay? B. B says, what is the probability that a worker is either sales and office or production and transportation. Okay? Total still the same, guys. It is still 126,172. This time we're looking for the probability. Okay, we've got an OR going on here, so we've got to do the general addition rule. So I have the probability of sales office, that's all one thing, or production transportation. Okay, so I know from my general addition rule that's going to equal the probability of sales office plus the probability of production transportation minus the probability of sales office and production transportation. Okay? All right, so we got sales office. What is the probability that a worker is either sales and office or production and transportation? Do we actually have to worry about here that probability of the and? The sales office and the production and transportation? No. Because look at your chart. If I'm talking about sales and office, this is green, right? And then I'm talking about production and transportation in blue, is there any number that I highlighted twice? Okay? So these two categories are mutually exclusive. You can't be in both. The way this table is set up, the way the poll was designed, the survey was designed, you can't be in sales and office and be in production and transportation. However, technically you could be, theoretically. But none of these people are in both. That's not the way that chart was set up. So, that's just, but if we followed the general addition rule, that's what we were supposed to do. But see, there weren't any crossovers. There's nobody that's going to be listed twice. So he's just going to be 0 is what that's going to come out in the end. But we'll fix that. Okay. So the probability of sales in office, so that's going to be the 22,352 plus the 7,352 all over 126,172. Okay? That takes care of sales in office. I made him green a while ago. So sales in office, this is sales in office. Okay? Plus, okay, products or production and transportation, which is 14,597 plus 1,308 all over 126,172. We'll make him blue, because that's what I highlighted him blue up there as. Okay? Minus that intersection, that crossover where we do sales and office and production and transportation, which, like you said, the blue never crosses the green here, right? You didn't write any number down twice in the numerator, did you? Remember a while ago we had 25 written down 2 times? Well, that's just 0. You can put 0 over 126, 172, but that's 0, guys. Okay? So what is that going to give me? I'm going to let y'all. It is 0.361. This first chunk is going to give me 0.235 plus, then the second blue gives me 0.126. Then I just have minus 0, and that does give me 0.361. Okay? Let's see how long C is. I probably need to put C on the next page. Yes, ma'am.
If I write it all out, adding everything, just dividing, just giving that same answer, I could do that every time?
Mhm.
Or before I have to follow these steps? Can I skip the 0 point?
Oh, no, you can just, you can type all that in the green and the blue in your calculator and then just write down 0.361. That's fine. You don't have to show me that the green is 0.235, the blue is 0.12. No, you don't have to show me that. You can just put it all in the calculator at once. There's nothing wrong with that at all. C. Okay. C.
Whoa.
What happened? Do I need to go back? Do I need to go back over?
Okay, so where did you get the 0.235?
The 22352 plus 73.
Okay, I was doing that.
Let me-
Okay, never mind.
Let me make him green.
Okay, I'm good.
Okay.
Thank you.
Yes. C. What is the probability? That a worker is either a college graduate or has a service occupation. Okay, so this is another general addition rule. Okay, so we want the probability that we're a college graduate or service occupation. So I'm going to say service. I know that's going to be the probability of college plus the probability of service minus the probability of college and service. So remember, that's our intersection. That's our overlap right there. Okay? So I go back and I look at the probability of college. We already added that up, didn't we? That was A, wasn't it? Was it A? No. Yes. Was it A? What's the probability that a randomly selected worker is a college graduate? So the probability of college from A was 43181. You know what though? I'm going to write it. You don't have to write it all the way out. I'm going to write it all the way out. I don't think I did over here on A, did I? No. I just told y'all to add that column up so that you can see that crossover. So what I have on that probability of college, let's make it blue. I've got 31103 plus 2385, and like I said, you don't have to write all this. 7352 plus 1033 plus 1308. But I do want y'all to see where that overlap is. 126172. Okay? This is the college graduate, probability of a college graduate. Okay? Plus the probability of service. Okay, that's 15967 plus 2385. Yeah. All over 126172. Let me make him green. Okay, can you tell me what the probability of college and service is? Who's the overlap? Who is the overlap number? 2385. Good. Minus 2385 over 126172. Now, you could see that if I flip back over to the chart, if I hadn't colored on it too much. I did a little bit. But I've got, here's my college in yellow, right? And then I'm gonna do, let's do in pink. And then I had service. So I'm doing pink and yellow. Where do I see both pink and yellow? Where did they overlap? On the 2385. So that's your service and college right there. Okay? This one. Here's my overlap for that one. Okay? Now you're ready. This one, the first part in blue. Let me make this. The first part in blue should be, we got what? 43,181 over 126172 plus, did y'all get a number for the green for me? Or did y'all just do it all together? Tell me again. Oh, all together? You just did it all together? Oh, okay. Because I just ran it all like together. 15,967 plus 2385, 18352. Okay. Over 126172, then minus that 2385, 126172. Okay. And that does come out, once you put it all together, did we get 0.469? Is that what y'all said? Okay. Okay. We can color him pink. Okay. Okay, let's talk about now. In this one, in C, they weren't what we call mutually exclusive. But in B, they were. Remember, we had the 0 for the and part. So, mutually exclusive, let's define that. We have two events are mutually exclusive if it is impossible. Oh my, did somebody fall down? For both events to occur. I'll shut the door. Mutually exclusive. Two events are mutually exclusive if it is impossible for both events to occur. All right, let's look at example 3. A college student is chosen at random. We're just going to say a college student is chosen. Event A is that the student is older than 21. Okay? And event B is that the student is taking statistics. Are events A and B mutually exclusive? So, college student is chosen at random. Event A is the student is older than 21, and event B is the student is taking statistics. So it's asking you, are they mutually exclusive? No, you can be 21 and taking statistics. You can not be 21 and taking statistics. They're not mutually exclusive. Just because I'm 21 doesn't mean that I can't take statistics. Okay? I did not take statistics when I was. I might have been 21 when I took statistics. Oh, I think I was. Took 401 and took calculus-based statistics. Took that in the summer.
Was
One
that
time.
like 50 years ago?
Oh, that's so rude. Your grade just dropped, Robert. It's like plummeted way downhill. No, it was like, so what, I was 21, so that was 26 years ago.
Nice.
Yeah. What was it, summer of 1999. Yeah. Graduated college in August of 99. Long time ago. Yes, it was before 2000. Oh my God. So this is a no. They're not mutually exclusive. Oh. If, and you guys proved this a while ago, if events are mutually exclusive, then the probability of A or B equals the probability of A plus the probability of B. Because remember a while ago when we tried to do the one that was mutually exclusive, and we did it by the general rule of addition, that we got 0 for the probability of A and B. So if they are mutually exclusive, you can just add the probabilities together. You just have to know when you're reading the chart or you're reading the problem if they are, okay? Okay, example 4. Oh, we're at the end of this one. Example 4, in a stats class, of 45 students. It's a big class. 11 got a final grade of A. 22 got a final grade of B. And 8 got a final grade of C. What is the probability that a student got an A or a B. So on the probability of A or B. So the first thing these days I need to ask myself, are those events mutually exclusive? Yes, you can't get an A and a B for the same course at the same time. Now, there are some people that if they made a B the first time, they didn't want a B, they wanted an A, they would actually go and they would fill out a little form and retake the class to try to get an A. But at the same time, they can't get both an A and a B. Like when you finish this class, you're not going to get A or B on your transcript. You'll get A or you'll get B, right? Or C or D or F or an I. You know. Anyway, so they are mutually exclusive. So I can just say the probability of A plus the probability of B will equal the probability of A or B. And I'll make a little note out there, since they are mutually exclusive, we can use that, okay? We don't have to do the minus the probability of A and B. Okay, so probability of A is going to be, how many got an A? 11 out of 45, plus how many got a B? 22? 22 out of 45. So that's really 33 out of 45, which as a decimal, that's going to be, we're getting about 73%, 0.733. 0.733. Okay. B. What is the probability? A student got an A, B, or C. Okay? So, once again, are they mutually exclusive? Yep, you can't get A, B, and C. So, this is going to be the probability of A or B or C is going to equal the probability of A plus the probability of B plus the probability of C. Okay, so the probability of A again was 11 over 45, plus the probability of B was 22 over 45. And this time we're going to add that probability of getting a C. And that was 8. 8 got a C. So that gives me 41 over 45. 41 out of 45, when I type that in and I get a decimal, it should be probably around 0.911. That's actually a very good success rate. That's what we call a success rate if it's A, B, or C. That's not necessarily the pass rate. Pass rate for courses that allow you to have a D. And so a pass rate is considered A, B, C, D, and a success rate, it measures A, B, C. You're successful. Okay? 0.911. If, last little definition here of the night. I know, it's 8:35. We don't have to do example B. 5. If A is any event, the complement of A is the event that A does not occur. The complement of A is denoted A with a little c at the top, okay? Either A or A complement must occur. Okay, guys, something has to happen. A and A complement are mutually exclusive. Now, you will have problems that involve these next two equations. I have the probability of A plus the probability of A complement has to equal 1. Guys, that makes sense. If you add the probability that it does happen to the probability that doesn't happen, that makes the whole 1. That makes 100%. If you got a 50% chance of getting heads and you got a 50% chance of not getting heads, that means you're getting tails. Add those together, that's 100% of what you can get, right? Makes sense. We can rework this around and we get the probability of A complement, and this is what you will use on some of your problems. The probability of A complement actually equals 1 minus the probability of A. Okay? This right here, this one, the last one that I just wrote, this is known as the rule of complements. No one, I can't fit that in there. Okay? I will just add example 5 onto the notes that I post, and you guys can go, because I know it's 8:40. Okay? I'm not going to keep you past what you have to. You guys can go ahead and go. Example 5 says the probability of A complement equals 0.27, and it wants me to find the probability of A. I use that formula that I just had, where the probability of A complement equals 1 minus the probability of A. So I have 0.27 equals 1 minus the probability of A. Okay? So pretty much when you move things around, the probability of A is going to be 1 minus 0.27, which gives me 0.73. There we go.